Hi everyone. In the last few episodes, we have analyzed how particles are represented by kets in a Hilbert space, and taken a look at some of the mathematics involved in working with these kets. In this episode, I want to move on to the second half of our framework, how we represent physical quantities. In the very first episode, we posited that physical quantities are represented by linear operators on our Hilbert space. Now we are going to further develop this idea and formalize it in mathematics. First, we are going to change our language a bit. We are going to use the word observable for any physical quantity that we can measure out of our particle. This includes position, momentum, energy, angular momentum, or any combination of those. Basically anything we can measure and therefore observe from our particle. Before digging into the nuance of how we represent these observables as operators, I want to remind ourselves about the formal definition of a linear operator just to make sure we're on the same page. As you might remember, a linear operator is a map on a vector space that preserves the linear structure of that space. In other words, a linear map satisfies the following properties. Addition is still addition, and scalar multiplication is still scalar multiplication. Note that a linear operator is an abstract map, while a matrix is a representation of a linear operator in a particular basis. We'll see in a bit that quantum mechanics has no standard basis, so that's why you almost always see us working with the abstract operators themselves. Moving back into quantum mechanics, we established that we suspect physical observables are represented by some linear operator on our space of kets. Now let's finally start digging into this idea. First, given an observable operator, how would we get the possible values that we can measure? To begin solving this problem, let us look at angular momentum as an example. Say we have a particle and an apparatus to measure angular momentum. We can take a measurement and know that at this moment, the particle has an angular momentum of 1.41 Newton meters seconds. Therefore, at this very moment, the particle has to be represented by a particular quantum state that corresponds to having that outcome of angular momentum. I mean, think about it. The measurement told us what the angular momentum is, so we can't be in a superposition of more than one outcome. Our particle has to be in the state representing this outcome. If instead the apparatus told us the particle had an angular momentum of 2.44 Newton meters seconds, then the particle would be in a quantum state corresponding to that outcome. Hopefully you see that this would be true for any possible angular momentum we could measure. So what we have is a list of possible measured values and associated kets, representing states that 100% have that value. We call these special states definite states. In these special states, our particle has a definite 100% certain value for angular momentum, no ifs or buts. Now, how would we get this list from the angular momentum operator? Well, we have a list of definite angular momentum kets and associated values. I don't know about you, but to me, this screams eigenvalues and eigenvectors, and this is the right direction to head. Most textbooks just state this as a fact, but hopefully you see why it's incredibly reasonable that eigenvectors show up. So, let's summarize the conclusion. Every physical observable is represented by some linear operator in this vector space. To figure out all the possible values of that observable, find the eigenvalues. To figure out which state corresponds to having that particular value, find the eigenvector corresponding to that eigenvalue. These eigenvectors are called eigenstates, and represent definite states that 100% have this value for the observable. This is the fundamental framework for how we represent observables in quantum mechanics. Now let's relate this to our current understanding of quantum states. Ever since the start of the series, we've wanted to represent our particle as a superposition of all possible outcomes of a measurement. We now finally have the framework and language to do so. We now know that these outcome states are actually the definite states of the observable, which are its eigenstates. So, mathematically, being in a superposition of outcomes is done by being in a linear combination of an observable's eigenvectors. Now, note that we haven't discussed how the coefficients relate to probability, or what happens when we actually take the measurement. Don't worry, we'll discuss this in depth next episode, where we derive the Born rule. Now, with just this, we can already use our physicist's intuition to derive the mathematical properties that physical observables should have. First, observables need to have real eigenvalues. Intuitively, it doesn't make sense for a particle to have 2 plus 3i energy. Physical quantities are inherently real. Next, observables' eigenstates must span the entire vector space. Remember that the span of a set of vectors is the subspace formed by all possible linear combinations of those vectors. So this property says that linear combinations of an observable's eigenstates cover the entire quantum vector space. Another way to word this is that any quantum state can be written as a linear combination of eigenstates. This property actually isn't that hard to prove. See if you can do it by considering what it physically means for a particle to lie outside the eigenstate span. Give it a shot? The key is to realize that every single particle has a value for an observable. Meaning every particle has some value for position, for momentum, for energy, etc. So, for example, there aren't any particles that have a position of none. Taking that idea, let's imagine that the energy eigenvectors didn't span the entire space. This would imply that there was some quantum state outside the span, and therefore could not be written as a superposition of the energy eigenstates. So this quantum state has no possible energy measurement outcomes, since remember that the eigenstates represent the definite states you get from a measurement, and this quantum state can't be written in terms of any. But this isn't possible. The particle has to have some value of energy when we measure it. Thus, it must be in some superposition of energy eigenstates. This must also be true of every other observable we can measure. Therefore, the eigenstates of an observable must span the entire space. Lastly, we can actually conclude that the eigenstates must be mutually orthogonal, i.e. perpendicular. We can use the arrow analogy to see why this is true. Here we have non-orthogonal states L1 and L2. Since they aren't orthogonal, we can decompose L1 into two components. One component along L2, which we can write as some scalar times L2, plus some orthogonal component. Remember that we define the definite states to be states where we are 100% sure the particle has that value for the observable. Yet here we have that the L1 state contains a superposition of the L2 state, meaning there's a chance we could get L2 if we took a measurement. This doesn't make any sense and goes against how we defined these definite states. Therefore, the eigenstates from an observable must be mutually orthogonal. A quick note, you may have noticed that we implicitly assumed that components should be decided using orthogonal projections. In the next chapter, we'll justify this claim. So we have found that an observable's eigenstates must satisfy two things. 1. Span the entire space, and 2. Be mutually orthogonal and hence linearly independent. What do we call a set of linearly independent vectors that span your space? A basis. And because each state can be normalized, we just showed that an observable's eigenstates must form an orthonormal eigenbasis. We assumed this previously, but now you see how we use our intuition to prove it. So let's summarize a bit. In quantum mechanics, all physical observables are represented by a linear operator. By just considering physical intuition, we found that this operator must have an orthonormal eigenbasis, representing the definite states of this observable. The corresponding eigenvalues must be real, because they represent the values that we would measure in the corresponding eigenstate. If you've taken a quantum mechanics course in the past, these properties are usually derived by assuming observables are Hermitian operators. But haven't you wondered why we assume them to be Hermitian in the first place? In this approach, we get these properties just from physical intuition, and in Chapter 9, we'll show how these properties actually imply that observables are Hermitian. Now, there are still open questions. Most importantly, how do we calculate the probability associated with measuring each eigenvalue? We'll answer this and derive the Born rule next episode. There, we'll connect everything together and lay out the full prescription for our mathematical model of quantum physics. Thank you so much for watching.